Okay, we're going to start today a rather abstract and, in some sense, tedious chapter, which is second quantization, which is, however, useful in a few contexts of theoretical physics. So maybe it's a good idea to see it sometimes. It is useful when you have to do calculation or theories for more than one electron. Okay, for two, you can really go along with the first quantization treatment, as we have done last time for helium. Okay, you write your Slater determinant. There are just a few two terms essentially, and two terms they can be handled, no problem. But when the number of particles starts to be large, working with those objects that we introduced, so sum over permutation of objects, is quite heavy. I mean, it becomes very, very involved. So let me remind you the problem. So you have sum Hamiltonian, okay, which is sum over several particles. For instance, when we discussed helium last time, it was p squared over twice the mass minus z e squared over ri, okay? This would be the parts in which the electron interact with a common nucleus, okay? So there is a common nucleus of charge Z, and you have several electrons. So maybe I'm trying to describe an atom, okay? But more generic than just helium. And then I would need to add a term like this, sum over I different from J, E squared over Ri minus Rj, okay? So if I was able to solve a problem like this, for any n, then I would generate the periodic table, essentially, okay? So that's quite an important problem in some sense. So how one adventures in doing these things? Well, we said one thing is that the states, okay, being states of fermions, have to be correctly antisymmetrized. So you do not work with product state, or better yet, you sum over many permutation of product states with the appropriate sign. So typically, for instance, you would write Slater determinant states. So let me repeat, you take a single particle basis of your choice, okay? For instance, hydrogen-like orbitals in the present case. But there are people who like working with plane waves, even to describe molecules and things like this. So it's rather an arbitrary choice at this point. As long as the basis is complete, you can describe any problem with any basis, okay? So let me just indicate with alpha. So this is the basis set to describe the Hilbert space of a single particle. Obviously, then we want to describe Hilbert space of many particles, H2, Hn, and we said that what we can do is, for instance, to write states like this, equal to the sum over all permutations of -1 to the p, alpha p1, 1, alpha pn, n. And here, in order to normalize everything, I just put 1 over square root of n factorial, okay? I have specialized the thing to fermions, okay? For today's lecture, I will just pursue fermions only. Next time, I will tell you the few things that you have to change if you want to deal with bosons, okay? Well, one obvious thing is that there is no sign here. This might seem like a simplification, which it is. However, Pauli principle is not there, so more than one time the labels can appear in the thing. Also, the normalization has to be taken care in a special way. So there are a few changes here and there. But the main changes is that the basic objects that we will introduce, which are, just to anticipate a little bit, creation operators and destruction operators, okay? We will see that for fermions, you do have rules like the anti-commutator of A and A dagger, okay, which is something like this, okay, is equal to 1. While for bosons, you have the more known rule to you, perhaps the fact that the commutator, okay, is equal to 1, okay? So this is the boson case, and this is the fermion case. So we'll see this thing next time. This is, by the way, what we have already seen for the A and A dagger in the harmonic oscillator, except for now the presence of an extra label alpha, because now we have a basis that is labeled by a certain alpha, and you will introduce an A dagger for each alpha, okay? Not a single one, but one for every element of the basis, okay? But for the rest, the basic objects that you introduce is pretty much similar to the A and A dagger you have worked on in the harmonic oscillator, okay? For fermions, we will introduce a similar objects, but there is a crucial difference, and the crucial difference is that the basic things are related by what is called an anti-commutator, okay? You see with this curly brackets, I indicate exactly the thing that is upstairs. So not the commutator, but with the commutator with the wrong sign, with a plus in the middle, okay? And we will see that the similar thing happens, well, we'll see in a second, okay? So this is just in perspective what we will do today and next time. But let me continue with a bit of perspective. Why do we want to introduce these objects to describe the theory? Well, it would be very nice, okay, if rather than having this cumbersome sum over permutation, I might simply worry about which labels are there, okay? So in some sense, since the labels are in the end summed over, and shuffled and permuted all over, the important information there is which ones are present and which are not, okay? So the mere presence or absence of a label is somehow the important feature of the state, not so much the fact that alpha 1 is associated to particle 1 or alpha 3 with particle 3, because as you know, really everybody shares labels, okay? So it's the fact that a certain label is present or not the important thing. So we'll try to describe this in a more formal way by saying that we obtain the state by creating, okay, with this operator, creation operator A alpha, the labels on the vacuum. Well, this is, we will see it in a second, just to give you the perspective. So the state, in the end, will be written in a simple way, just product of a few A daggers applied to a vacuum, okay? Which is much simpler than sum over permutation things, just a product, a single one. However, in order to be correctly antisymmetric, obviously these objects, which appear as a simple products, have to be subtle in when you permute them. Okay? So for instance, if you exchange two of them, obviously you must have a minus sign. Okay? So in some sense, what is non-trivial in their nature is the fact that A, say, alpha 1, A dagger alpha 2 must be equal to minus A dagger alpha 2, A dagger alpha 1. Okay? So if you exchange them, you get a minus sign. They do not commute, they anti-commute. Okay? And this minus sign is what you need to make the state correctly anti-symmetrized for fermions. Okay? This is one feature. The second feature is that you will need to express not only the states in terms of these objects. By the way, this way of writing states and operators is called first quantization. Okay? First quantization. It's the standard approach. Okay? So when you say I write it in first quantization, it means I write a later determinant wave function, I write an operator like sum over n, and so on and so forth. Okay? The second quantization involves these creatures here, okay, which somehow are able to create a state and make it already nicely anti-symmetric. But there is still, yes?
Is anti-commutator for is it one or?
Which one? If the two things are, I mean, this is the anti-commutator between two A daggers. This is the anti-commutator between an A and an A dagger. It's yeah, with the same alpha. If it is different alpha, you will get 0 there. We'll see them. I mean, it's just to give you a glimpse of what is going to come, okay? So not only I need a way of writing the states, I need also a way of writing the Hamiltonian, for instance, or any operator. Because after all, it's all a business of calculating expectation values of things, okay? So I do need to express both the states and the operators in terms of the new actors, okay? So we will need both, not only the states. And we will see that there is a way of writing, for instance, this piece here, okay, in terms of them, okay? But wait for a second before we will see the solution of this problem. Okay, so this is what we want to do, to introduce new objects which formally simplify the writing of states. But obviously, I mean, they do not have to change the numbers, okay? So if I calculate a certain expectation value of this Hamiltonian into, say, a given Slater determinant, well, the new way of writing should provide exactly the same number. So it's kind of a mapping, okay? You write things in a new way, but in such a way that the numbers come out to be exactly the same, okay? You don't want to certainly introduce new physics. All right. Okay, let me just start slowly. Okay. So for every alpha in the basis, okay, you can always think of introducing an operator, A dagger alpha, which does the following. Well, formally, you introduce actually two things. You introduce a state, some reference state, which you call vacuum, okay? A state where there are actually no particles. And an operator, A dagger alpha, which creates a particle in state alpha, okay? So according to my old way of writing, this would be just a single particle state alpha, okay? The state of the basis. Is this clear? So each alpha is obtained. So here I have all the states, okay, in my Hilbert space, okay, of a single particle. Well, I take a reference state, which I call the vacuum, and I obtain each one of them by applying this operator, A dagger alpha, okay? Creation operator. Well, this is just, I mean, a formal object, obviously. Doesn't mean much up to now. Well, obviously, that's not enough. We want to be able to describe states with many particles. And formally, what you can say is, suppose that I have already defined states like this. Then what I define is that A dagger alpha is simply a state of that form where there is alpha in the first position, okay? So now A dagger alpha is defined not only by acting on a reference state that I invented, but also by acting on a given anti-symmetrized state. So A dagger alpha does two things. First of all, it creates the label alpha. You see, alpha is there, is not there. Second, it makes the resulting state anti-symmetric. Okay? This is some kind of magic. So we have to understand what it really does that object, okay? So this is kind of definition, okay? A dagger alpha is an operator which creates the single particle states out of a reference vacuum and also is able to add one label to an already antisymmetrized state by making it fully antisymmetric, okay? Now, which properties do the A dagger alpha so defined should have? Well, first of all, you realize by mere induction that evidently A alpha 1, A alpha n is simply obtained by creating one by one the A dagger that you see, okay? So you do A dagger alpha 1, A dagger alpha 2, up to A dagger alpha n on the vacuum, right? You realize that this is the induction mechanism that is there. You first create particle alpha n, okay? Then you add particle alpha n minus 1, and you antisymmetrize, and you get, okay? So you get first this. Then with the next one, you get alpha n minus 1, alpha n, and then so on and so forth until you get alpha 1, alpha n, which is what we want. Okay? So this is the process by which the operators increase the labels. Now, evidently, as I discussed a moment ago, these A daggers are, I mean, they have certain commutation properties that are pretty special because this state is totally antisymmetric. Okay? In particular, if I exchange two labels in the states, I should obtain, for instance, a minus sign. Okay? So suppose that I consider now alpha 2, alpha 1, alpha 3, alpha n, okay? Where here I have alpha 1, alpha 2, okay? So on one hand, I know that this must be equal to minus alpha 1, alpha 2, okay? According to what we have said in the preceding lectures, okay? On the other hand, the first object is equal to A dagger alpha 2, A dagger alpha 1, A dagger alpha 3, and so on until you have A dagger alpha n. While the second is equal to A dagger alpha 1, A dagger alpha 2, A dagger alpha 3, and so on, okay? And there is an extra minus sign, so this is equal to minus that, okay? Oops, I did it wrong here. So you see that these two objects are the same, okay? But what you have here and what you have here have to match, okay? So immediately you notice that a simple permutation of two of them costs you a minus sign. All right? So you conclude the first thing is that A dagger alpha 1, A dagger alpha 2 is equal to minus A dagger alpha 2, A dagger alpha 1. In other words, the order in which they are applied matters, okay? And it matters with a minus sign. Another way of writing this is that if you bring this on the first hand side, it becomes a plus, and this becomes 0. A further way of writing is to introduce the symbol of anti-commutator. So the anti-commutator of two operators is AB plus BA rather than the minus with the commutator. And you see immediately that this is simply that the anti-commutator of A alpha 1 and A alpha 2 should be equal to 0. Okay? So the fermionic creation operators are such that they anti-commute with each other. Here, alpha 1 and alpha 2 are two arbitrary labels, obviously, so all of them have to commute. All right? Okay. In particular, obviously, this already implies that if alpha 1 and alpha 2 are the same, you see immediately that this implies that A dagger, so suppose that they are the same label, alpha, A dagger alpha is equal to minus A dagger alpha. So you see when the two labels are the same, this operator creating twice the same label is equal to minus itself. It means that it must be 0. Okay? So Pauli principle is again recovered, no surprise, in this scheme. Okay? So the anti-commutation embodies the change of sign and Pauli principle in a straightforward way. Okay, so this is simple. By the way, just make a mention here. If you had bosons rather than fermions, what would change is this minus sign. There's no minus sign there. And therefore, for bosons, I anticipate, you get here the correct minus sign, and therefore the correct, say, anti-commutator. So this becomes the commutator now. A dagger alpha 1 commutator A dagger alpha 2 is equal to 0. Okay? This is just to make clear that the change in this case is very, very simple. Commutators instead of anti-commutators. Okay? Obviously, there's no Pauli principle. You can have the same label twice. Nothing forbids that. Okay. How do we proceed? That's obviously only the first step. A dagger seems to allude to the fact that there is an A. Seems to be the adjoint of something. Now, what would be the action of A? A is clearly a destruction operator. A dagger creates, A destructs, destroys. Well, the way to define it properly is, you remember always that we did it when we discussed Hermitian operators and Hermitian conjugate operators. The idea is the following. If I have some operator here, okay, some A alpha, acting on a certain state psi 1, okay, and you calculate a matrix element with another state psi 2, you know that this must be exactly identical to having the A dagger appearing here on the left, okay? So this is, in fact, a nice way of defining what A alpha does, okay? A alpha is that operator such that when acting on the right on a state psi 1 does exactly the same thing that his partner A dagger alpha does, okay, acting on the left, okay? So this is a very natural thing, okay? So let us see what properties A alpha have. Well, first of all, you see immediately that A alpha acting on the vacuum, on the reference state, this time must give us 0. Let's see this first simple property. This is the 0, not the vacuum, okay? It's just a standard 0, the Hilbert space 0. It's 0. Okay, how do I prove this first thing? Well, let me just do it here. I just use this, okay? Now, let me put any state psi 2 there. Now, this means A dagger to the left, psi 2 with a vacuum. Now, obviously, this state here has whatever particles are there. Psi 2 might be a state with, say, n particles. This has n plus 1 particles, okay? On the left, there's nothing, just a 0, okay? So the most you can go down in number of particles is when this has no particles. But even then, this has 1 particle in alpha, okay? So obviously, this thing will always be 0, whatever psi 2 you take, okay? So it is an obvious thing. You cannot destroy things where there is nothing to destroy, okay? Essentially, this is what this equality is telling you, okay? So A alpha, unlike A dagger, destroys the vacuum, while A dagger creates a particle with alpha on the vacuum. Now let's consider the more interesting thing. Suppose that I have A alpha acting on a certain state, alpha 1, alpha n, and suppose that alpha is not present in this list. Okay? So we'll do several cases. There are essentially two possible cases, or perhaps three. Alpha is not present there. Second case, alpha is present there in first position. Third, more general case, alpha is present there in a generic position. Okay? We will see these three cases in turn. Okay, so let us start with the first. So alpha does not belong to the list of labels alpha 1, alpha n. Okay? Very well. Then let's use our, so now this Ci1 is simply alpha 1, alpha n, no longer the vacuum. And this is alpha 1, alpha n. Okay? So the action of A alpha on this object must be exactly the same as the action of A dagger there. So suppose that psi2 is some state like, well, how many particles there must be in psi2? There are n particles there, so n minus 1 particle must be in psi2, and one more is created by alpha. Okay? So let me write psi2, okay? I write it as alpha prime, say, let me call it just 2, alpha prime n. I start from 2 so that I remember clearly that there are one less rather than 1. I could start from 1 and get n minus 1, but it would be more handy to start from 2 and end up. I put the prime because they are generally different from the alpha that I have on the right. Okay, they are new labels in number of n minus 1. Okay, so that's any generic psi2. Okay, now what is this object here? Well, the object there is A dagger psi2. So it's a state that is, alpha prime 2, alpha prime n. Now you understand why I got the first position I put 2, so that I can put the A dagger immediately in the first position there. Okay? Good. So this is obvious what it is this state. Okay? This is, sorry, I don't want to put this. This was the previous case. Okay, so this object here is equal to alpha 2 prime, alpha n prime, scalar product with alpha 1, alpha 2, alpha n. Okay? Now, you immediately see that the labels that you have here on the left are certainly never equal to those labels. Even if the alpha prime are chosen in such a way that they are essentially the labels that you have there, you see that this label alpha is never appearing on the right. Okay? So these are two states in which one of the labels on the left differs, okay, not only in the position, it differs because it's not present in any position on the right, okay? You can prove, well, by simple arguments, just using this expression, okay, that whenever two states, okay, you take the scalar product with alpha prime and alpha n prime, two states are such that even a single variable there differs, a single label differs from the other one, okay, you get 0. Okay? The only case where you do not get 0 is when these labels here are just a permutation of the others. Okay? Permutation is irrelevant, you know, it gives only a sign at most. But the difference even in a single label is such that one term in each single sum will get you a 0 overlap because of orthogonality, okay? So it's a very simple thing to prove. Two Slater determinants which differ even by a single label, which is present in one case and not in the other, will be orthogonal, okay? And therefore, this, okay, is certainly 0. In other words, if you try to destroy the label alpha in a state which has no alpha, you get 0. Good. This is reasonable. Okay. Second, suppose that alpha is there, and suppose it is there in first position. So I do now the case alpha belongs to the alpha 1, alpha n, and in fact, let me assume that it is in the first position. So the labels here are alpha, alpha 2, alpha n, okay? So it's just in the first position. Then I want to show to you that this time is not 0, the result. This time, the result will be an anti-symmetrized state where essentially the first label disappeared, okay? So to remind you that there was a label and I have just make it disappear, I put the alpha with the hat on top. Hat means it's not there. It's like a cross, okay? Alpha 2, alpha n. Okay? So let me just show this to you. It's a very similar proof. So what I do is now I have alpha, alpha 2, okay? Alpha, alpha 2, okay? So on the left I have alpha, alpha 2 prime, and on the right I have alpha, alpha 2, okay? So you realize that this now can be different from 0. Certainly alpha is there and there. When this will be different from 0? When these labels here are just a permutation of these labels here. Okay? So this element here is, generally speaking, equal to 1 or minus 1, depending on the order in which this alpha prime, okay, are with respect to the alphas, right? So in particular, if the alpha 2, okay, alpha n are exactly the ones that you have there, then there is no order whatsoever that you need to worry about. This object is exactly 1, okay? So you realize that this is exactly somehow the same thing as not having alpha at all, okay? So in some sense, if I drop alpha from the list, okay, the resulting matrix elements are exactly the same. I should not care only about this diagonal one. I should really put the prime here. For the things that are different, I get obviously not 1, but I get minus 1 to the appropriate permutation, okay? So if I have, there are really 3 possibilities. One, they are exactly the same. They are just a permutation, or they differ in some case where I would get 0, okay? And you realize that this is exactly the same thing as just dropping the alpha from the list. Because even in that case, I would have either 1, a certain permutation, or 0 if these elements are not a permutation of that, okay? All right. In other words, this is telling you the following. Let me write it a bit more clear. This is telling you that if I have A alpha acting on a state that is A dagger alpha, first position, then A dagger alpha 2, A dagger alpha n, then destroying alpha after you have immediately created it, it's like dropping alpha altogether, okay? So the result is just this. However, the most general case is the following. Alpha is present, maybe, but not in first position, okay? So for instance, suppose that alpha is present at a certain position, alpha I, okay? So from the list there is a certain element which matches alpha exactly, okay? So alpha is in position alpha I. Then what you are calculating is this: A alpha, A dagger alpha 1, A dagger alpha 2, A dagger alpha I, A dagger alpha n to the vacuum. Now, how can you proceed now applying what we just learned? Well, it's very simple. You have to bring this here first, because I know that this is equal to alpha. Okay? So I can pay a certain number of minus signs. How many? Okay, in order to bring this to the first position, I have to pay a certain number, I minus 1 of minus signs. Okay? So I have minus 1 to the I minus 1. And in this way, I can bring this there. Okay? So to make things perfectly clear, this object here is exactly identical to minus 1 to the I minus 1, A dagger A alpha, A dagger alpha I, A dagger alpha 1, A dagger alpha 2. Now, nothing in position I, and again, A dagger starting again until n. Okay? So you see that now, since alpha I is equal to alpha, I can apply the previous rule, okay? And I get these two going away, okay? So the rule is, if alpha is not present, you get 0. If alpha is present in a certain position, you can simply drop that creation operator, but you have to remember that there is a possible sign to pay, which is minus 1 to the number of jumps that you have to do to reach the creation operator that you want to destroy. Okay? So practically, the problem is very, very simple. You have a certain thing to destroy, and you have certain A dagger, alpha 1, alpha I, alpha n. Okay? Now, if alpha is not present there, you can essentially travel all the way to the vacuum, and you can use this, okay? And there is nothing that really saves this from being 0. Otherwise, if one of the labels is equal to alpha, okay, there is a certain number of elements that you have to jump over, okay? These elements will give you a factor minus 1 to the I minus 1, but after having reached the right position, you kill your creation operator with the same label, okay? And the resulting object is a state which has a hole in that alpha, okay? Is this clear? So to make it again clear, I mean, with the notation, I should write something like A alpha, alpha 1, alpha I, alpha n, okay, is equal to minus 1 to the I minus 1, alpha 1, alpha I missing, alpha n, okay? If alpha is equal to alpha I. Otherwise, you get 0. Okay? So this is essentially the whole story about A alpha. Destroys the vacuum and destroy, if present, a label of the same type in the list, okay? By just making, extirpating it with a possible payment of a minus sign. Okay. Now, with this, we are now ready to prove all the possible commutation rules that we need. Okay? So let's see. Yeah. Eh? Here? Should I what? Yes.
We have to cancel alpha I.
I'm canceling alpha I. Okay, so A alpha applied to this state where alpha I is present and equal to alpha will give me a state with one less particle. The alpha I is here missing. Okay, this means missing. And a certain sign, which is the number of labels that are just before the missing one. Okay, that's the notation. Okay, so let's see how I can now conclude on not just this commutation rule, but all the others that in principle you can write. So let's see. First of all, what about A? So the first rule that I wrote there is A dagger alpha 1 anti-commutator with A dagger alpha 2 should be 0. Okay? We said that this is due to Pauli principle and to, all right. What about A alpha 1 and A alpha 2? Okay? Now, not A dagger, but A anti-commutator. Well, you realize that essentially by taking the Hermitian conjugate of this rule, you get always this rule, right? You can prove this with the usual, I mean, A are nothing but A daggers acting on the left in some sense. So whatever A dagger does, A will do, okay? So if A dagger anti-commutes, the A anti-commutes as well. The crucial and more difficult point is what about A and A dagger together, okay? So what about, for instance, A alpha 1, A dagger alpha 2 anti-commutator? That is non-trivial, okay? And in fact, I will try to prove to you that this is equal to delta alpha 1, alpha 2. In other words, it's 0 if the two labels do not coincide and 1 if they do coincide, okay? So this is the non-trivial object that we will need to prove. And we have all the ingredients to show this, okay? Let's see. Let us start with the case where alpha is different from alpha prime. Okay? So suppose that these two are different, sorry. Actually, let me call it alpha and alpha prime, okay, like that, rather than alpha 1 and alpha 2. It's the same thing, obviously. Okay? So this is alpha, alpha prime, alpha, alpha prime. Okay, so let's see. Suppose that the two are different. Then I need to evaluate A alpha, A dagger alpha prime on one side, and A dagger alpha prime, A alpha, okay? I want to prove that these two things differ by a minus sign, simply, okay? If I prove that this is equal to minus that, then obviously, as a result of that, I will get that the anti-commutator is equal to 0, okay? Let's see. If I have this object, Let me act with this operator on any state. For instance, a state alpha 1, alpha n. Now, one thing. I know that alpha prime, in order for this result to be different from 0, must not be in this list, right? I can never try to create 2 times the same label. So first thing, in order for this to be different from 0, you must have alpha prime not belonging to the list alpha 1, alpha n. Okay? Clear? Otherwise, no. We said that if I try to do A dagger alpha 1 on a state that has alpha 1 already contained, okay, since this would be something like A dagger alpha 1, A dagger alpha 1, okay, the product of these two, since it must be antisymmetric, we said it here, okay? So this must be 0, okay? So this, I can never create 2 times the same label, okay? So this is what I'm telling you now, okay? Alpha prime should not be in the list. Otherwise, I would create it twice, all right? So alpha prime is not in the list. Okay, so this is Pauli principle. Very good. Now, if it is not in the list, I add it. So this is equal to A alpha, alpha prime in first position, and then I have alpha 1, alpha n. Okay? Then I have to destroy it. Well, in order to destroy it, it must be present in some position. Otherwise, I would get 0. It cannot be the first position, by the way. It must be some other position. Okay? So there must be some position here, alpha I, where, so there are 2 possibilities. One, alpha is not, so I should distinguish really. Alpha is not present, so is not belonging to the list, alpha 1, alpha n. Then, obviously, I would get 0, because I cannot destroy something which is not present. By the way, alpha prime doesn't help, because alpha prime is different from alpha, okay? So, I mean, if alpha is not in this list, would not also be in the complete list where you add alpha prime, okay? Good, so if this is true, then you get 0. Okay, if on the contrary alpha is equal to some alpha I, so this is equal to some alpha I, then what you have is a sign which is -1 to the I minus 1 plus 1. Okay? I minus 1 comes from here because there are I minus 1 things before, and there is an extra 1 because there was a new addition there. Okay? So these are the 2 possible results that you get. What about the other? Well, the other does the following. I have to operate on this object. Okay? So let's see. If alpha is not present, so first position, you get 0. Alpha not belonging to the list, you get 0. If, on the contrary, alpha belongs, and it is equal to some alpha I, okay, so second possibility, alpha equal to alpha I, what do you get? You get essentially a state in which alpha 1 is there, alpha I is missing, alpha n is there, times a sign that is -1 to the I minus 1. But then I have still this, A dagger alpha prime, okay, which I put again in first position. So I get -1 to the I minus 1, alpha prime, alpha 1, alpha I missing, alpha n. Is this clear? Okay? So the difference between these 2 objects, just to summarize, that in one case, I first added the label, okay, and then I tried to destroy the other one, which brought a number of signs that is I minus 1 plus 1, really, because there was a first object in front that I added. In the second case, the first object in front comes only after having destroyed, and therefore it has just a sign I minus 1. There's no plus 1, in other words. Okay? So you see that the two operations, okay, produce almost an identical result, which means having alpha prime present and alpha missing. However, they do it with a minus sign difference. Okay? Is this clear? So if needed, try to reconsider this again. And this shows that this is equal to minus that. Okay? So whenever you exchange two A and A dagger with a different label, you can do it, but you have to pay a minus sign. Pretty much the same thing as exchanging two A daggers. Okay? Same rule. Okay? Still, there is a price of minus sign to pay. Now comes the tricky thing. So when the two things are the same, there is not only a price of minus sign, but there is a 1 that is also in the game. Let's see why. Okay, so let us consider immediately the case now alpha prime equal to alpha. Okay, so I want to consider the action of A alpha, A dagger alpha on one hand, and A dagger alpha, A alpha on the other hand. Okay? Good. Now, this acting on a certain state, alpha 1, alpha n. Okay. First of all, what should I conclude about alpha and the set of labels alpha 1, alpha n? Well, alpha here cannot be in the list. Otherwise, I would get 0. Okay? So, two possibilities. Alpha belongs to the list. Okay? Alpha 1, alpha n. Then I get 0. Alpha does not belong to the list. Okay? And then in the action of the first, I do get alpha. Now in first position, then alpha 1, alpha n. Okay? Then I have to operate with the next one. Well, for 0, I still get 0. For this second, I get this. But now you see destroying alpha, after having created it immediately after, gives me alpha 1, alpha n. Okay? So, this object here, when acting on a state alpha 1, alpha n, has two possible results. 0 if alpha is not there. Okay? Sorry, if alpha is there. Because it would create 2 times the label alpha. And simply the same state, okay, if alpha is not in the list. All right? This is very simple. Now let us look at the second. The second distinguishes two cases again. Suppose that alpha belongs to the list. The other case is alpha not belonging to the list. Okay? As in the second. Now, let's do the second first. Because if alpha does not belong to the list, then this object here would kill the vacuum, right? So this would give me immediately 0. And there is nothing that can be done. I mean, a 0 is a 0. This is not the vacuum, okay? The vacuum might be resurrected by a dagger, but the 0 is a 0, okay? Good. So the second case is simple this time and gets 0. What about the first? Well, the first tells me the following. I have to destroy some alpha I. Evidently, if alpha is in the list, it must be in some position I. Okay? So the first part means -1 to the I minus 1, times the state where alpha I is missing. Okay? But then I have to recreate, okay, with this object in front. In order, however, to go there, to that position, remember, this is a state where I have a dagger alpha 1, then a dagger alpha I minus 1, nothing in position alpha I, again alpha I plus 1, a dagger alpha n, vacuum. Okay? Now I'm trying to add an extra a dagger alpha, which is the correct alpha I, indeed, but I add it here and I want to bring it there. How many minus signs should I pay? I minus 1, because it's this number of jumps that I have to make, okay? So the I minus 1 exactly cancels the first I minus 1, okay? So the result is now, again, the original state, because the I minus 1 is perfectly cancelled. Okay? Is this clear? Again? Okay, the destruction of A alpha from position I costs a sign in general, minus 1 to the I minus 1. However, luckily enough, the sign is completely eaten up by the corresponding creation of the object. I want to fill the hole that I have created, but the hole is in a certain position. And in order to bring this operator at that position, I should jump over many a dagger. Each jump, okay, by this property, costs a minus sign, okay? So the total number of minus signs that I must pay to bring this there is I minus 1, okay? So the I minus 1 from here is eaten up by the I minus 1 from there, and you have, in the end, a plus 1 sign, okay? So the result is, again, the original state, okay? So notice, the sum, in both cases, if I do A alpha, A dagger alpha, plus A dagger alpha, A alpha, and I act on any state, what I get? Well, in the first case, I get 0 from there and the state from the other. Okay? So I get the state. In the second case, I get the state from this and 0 from the other. Okay? So I get the state. So in both cases, you see that the equation you get is always this. Okay? One of these two operators is responsible for getting you the same state. The other one will give you 0. And which one gives you the state and which one gives you 0 changes in the two cases. So if alpha is there, something happens. If alpha is not there, the opposite happens. Okay? But in the end, the sum of the two, acting on any state, will give to you exactly the same state. And therefore, you realize that this must be equal to the identity. Okay? So this is what I wanted to prove. That the anti-commutator in this case is just 1. All right? So it's an exercise of minus sign, labels present, not present, killed. Okay? So it's a bit of, but, I mean, these things you do it one time now. Okay? Then you learn as rules and you operate on these things in an almost automatic way. Okay? So you know that you can move around these objects, A daggers and A, by just the usual rules of every time I jump, I pay a minus sign. If I have to exchange an A with an A dagger with the same label, I have to be careful. This is not only a minus sign, but there is a plausible 1. Okay? Pretty much as in the harmonic oscillator exercise, except for anti-commutators in place of commutators. Okay, so the algebra is pretty similar, and you can therefore kind of play with the objects in a very free manner, but remember that there is anti-commutators now. Okay, for the rest, this objects, in the way I have described, essentially encapsulate completely the properties of anti-symmetry that Slater determinants have in first quantization. Okay? They do exactly what they are supposed to do. They create labels, they anti-symmetrize. If you exchange, you pay minus sign. If the label is not present, you get 0. They do exactly what they should do. Okay? All right. One object that is particularly noteworthy is this. This operator, A dagger alpha, A alpha. Okay? Let us give a name to it. It's N of alpha. It's called number operator. Number operator. What it does? Well, you see immediately. If alpha is not present in the list, okay? So suppose that I apply this object to a certain state. If alpha is not present, we'll give you, let's see, we have done it, right? This one. If alpha is not present, we'll give you 0. If alpha is present, it gives you 1 times the same state, okay? So this thing will give you, when acting on the same state, will give you 0 if alpha does not belong to the list, and 1 times the same state if alpha belongs to the list. So in some way, this is like counting how many times alpha is present. Well, how many? Could be 0 or 1, okay? So it is a number operator. It's something that doesn't change the state, simply counts. If alpha is there, it gives you just a 1. If alpha is not there, it just gives you 0, okay? So it's a 1-0 counter, all right? That's the reason why it's called number operator. Now, for bosonic case, I must warn you, the state can contain the same label more than 1 time, okay? And in that case, this would really count how many times the alpha is present, okay? We'll do it next time. For the fermionic case, this how many times is 0 or 1, because Pauli forbids from having the label more than once. By the way, if you sum over all possible alpha, so if you do the following object, sum over all possible alpha n alpha, this object, when acting on any state, will give to you, as a result, simply n. It counts how many particles there are. Let me justify why this is so. It's very simple. Now, each one of them gives 0 for all the alphas that are not present, and gives 1 for the alpha that are present, okay? The alpha will be different, because there will be alpha 1 here, alpha 2, and so on. But therefore, in this sum here, there are an infinite number of terms that will give you 0, but there are n terms, exactly the one with alpha 1, alpha 2, and alpha n, which will give you a 1, okay? You sum those 1s, and you get just n, okay? So this operator here is nothing but the operator that describes the total number of fermions, okay, in the state. Now, this you might say, okay, this is trivial, because after all, it's n, it's fixed. But remind you that perhaps you have heard of grand canonical ensemble, okay? In the grand canonical ensemble, you do not fix the number of particles, which can fluctuate. And therefore, in some cases, it's useful to have an object that counts the number of particles, okay? Because this might be fluctuating from state to state, okay? So, I mean, it's just a parenthesis. This is a very simple thing, just an almost trivial object, okay? The sum of all number operators is the number of particles operators. Okay, what else should I tell you? Well, still a few minutes. Let's adventure in the following thing. I have selected a certain basis alpha, and I have constructed with that basis a certain A dagger alpha, which does what I have written there. But what about if I select another basis, beta or whatever? How the new operators that I would form with this new basis are related to the old ones, okay? Because that's an important thing, okay? Now, so suppose that I do the following. I define now a new basis rather than alpha. Let me call it I, okay? I is not necessarily an integer, it's some label, or you could call it beta, or whatever, okay? Some other label. Well, this new basis is obviously always related to the old one. Now, how can you write the relationship between I and alpha? Well, one way is the following. Write this as identity times I. Now, the identity can be written in many possible ways, and one way is sum over alpha, 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 okay? The usual trick, I. Now, you see that these objects here, okay, call them U alpha I, are some matrix elements, okay, of a matrix. Well, then this object is simply equal to sum over alpha, the alpha times U alpha I. Now, these matrix elements are a matrix that change the basis from one orthonormal basis alpha to another orthonormal basis I. No surprise, they are unitary matrices, okay? Pretty much as you have when you change basis in between orthogonal states in, say, R3. Then you have essentially orthogonal matrices, real one. Here you have complex objects, so they are unitary rather than orthogonal, okay? So you can prove, I mean, that that these matrices here are such that U dagger U is equal to the identity, okay? So please try to see if this is clear to you. Okay, so you know what I is in terms of alpha. It's just a combination of alpha with some elements of a unitary matrix. Well, but then you know that A dagger I applied to the vacuum, which is this state, is equal to sum over alpha A dagger alpha applied to the vacuum times U alpha I. Okay? I've simply rewritten this as A dagger alpha to the vacuum and rewritten this as A dagger I to the vacuum. So there are two objects now, the A dagger alpha for the first basis and the A dagger I for the new basis. Evidently, they must be related. And you see that by acting on the vacuum, they are, I mean, they give you the same thing, and evidently there must be a rule, like A dagger I is equal to the sum over alpha of A dagger alpha U alpha I. Okay? So if you change basis with a certain unitary matrix U, okay, like here, like in the first line, then the corresponding operators that create the new basis is related to the old one by the same matrix U. Okay? Obviously, you can take the adjoint of this, for instance, and you can prove that Ui is equal to the sum over alpha of A alpha U star alpha I. Okay? This is just by taking the adjoint of the first. So both A daggers and A are transformed into this way. Now, perhaps I still have some spare minutes, yes, to tell you one particular basis that is often used. Well, or sometimes, especially to write the operators, is the famous real space basis, okay? After all, that is a reasonable basis that you can start and be willing to use. You know, it's a little bit pathological. They are localized things, so in some sense, they do not have a norm that is finite, but still they can be used to express any wave packet, okay, by appropriate integral, pretty much as the plane waves are also a little bit pathological, but they are good as basis state to express in Fourier transform things, okay? So in the same spirit, the localized states are useful. And you can write the relationship between the localized states and any other state. So first of all, if I is a localized basis, the corresponding operator, A dagger I, is given a special name, okay? Is called field operator, okay? So whenever I create a particle at position r and spin sigma, I call that particular A dagger I call psi dagger sigma r. The notation is slightly different, but is almost universally used. That's the reason why I introduce it now like that. These are called field operators. They should not be confused with wave functions in first quantization. So it's not the wave function of a single particle. It's an operator. It's like the A dagger. You see there is a dagger, by the way. So it's not just psi. The psi that we have introduced since the first lecture is nothing but the creation operator for creating a particle in a certain position with a given spin. All right? So it's the creation operator associated to this particular choice of basis. But clearly, by the same reasoning we made here, we can find relationship between this and any A dagger that we might want. Okay? Let me repeat for you the idea. The idea is once again that R, single particle state, I'm trying to repeat for you this, okay, is equal to sum over alpha of alpha alpha R and sigma. Okay? But this is nothing but the sum over alpha of alpha. Let's see. I do have some wave function here, phi alpha star, because this is really the star of the wave function, times a delta function for the spin of alpha and sigma. So times delta sigma sigma alpha. Okay? So this is simply the relationship between position eigenstates and generic eigenstate alpha. You have to know the wave function of the generic eigenstates, and then the relationship is like that. Okay? Now, this is just psi dagger sigma r applied to the vacuum. This is A dagger alpha applied to the vacuum. And therefore, what you have is that this is equal to the sum over alpha, this times phi alpha star r, delta sigma sigma alpha. And you immediately see that this object have to coincide. Okay? So the field operator is nothing but a sum over all possible alpha of A dagger alpha weighted with the wave functions of the alpha states, okay? And obviously with the same spin, okay, as the one you want to create. All right? So it's a rather, I mean, it's an operator, first of all, so it's not a wave function that you plot. And in principle, it's not clear from what I've told you till now what is useful for, okay? It will be useful because we will see that in terms of it, it's very simple to write the Hamiltonian in second quantization, okay? But we will see this, I would say, next time, because I realize that the formal machinery is kind of dry and heavy and perhaps rather new. So I don't want to overdo it, otherwise I kill you, okay? Good. So next time we will learn how to write the operators, not only the states, and then we will do also the bosonic case as an example.